Hi, in this video, we're going to talk about the Grover search algorithm. Now, searching is a very important problem in computing. You have an unordered list of n elements. So the list is n elements. And let's say some of the elements are marked. We have m marked elements. And let's suppose that m is very, very less than n. And you have to find one of the marked elements. Now, to find these marked elements, you have to query the list or query the database. And the question is, what is the best you can do to find one of these marked elements in terms of the number of queries? So find the marked elements with a minimum number of queries. And as you may know that for a classical search, you require order of n queries to search a marked element. Now, the Grover search algorithm is a quantum algorithm that does a quadratic speedup over the classical case. So, quantum Grover's algorithm requires only order of square root of n queries to the database. All right. So, now let's look at the Grover search circuit. So, the circuit is quite straightforward. It looks the following. So, you have a set of qubits, and you have so these are the top qubits, and you have the Hadamard gate, and the qubits are initialized. So that's the first part. And after this point, you have a series of applications of what is known as the Grover operator. So this is and so on. These are the same operators, G. So several applications of them. And then finally, you have a measurement of the top set of qubits. And you should get the answer at the end of this measurement. So now the number of elements in our list or database is n, and it is related to the number of qubits is 2 to the power n. All right. Now, we need a sort of a quantum version of the query. And in the classical case, we can say that if X is an element which is marked, then there is a query function f of X is equal to 1 if X is marked and is equal to 0 if it's unmarked, right? So that is our classical query function. And as you know, you have this corresponding version u of f, the quantum version. So u of x acting on ket x is equal to -1 to the f of x, just like we had in the earlier algorithms. Now the Grover's operator consists of two operations. So G, I can write G as this u of f, and then followed by this R psi. So U of f is the query to the database, and R of psi is um, an operation And in this case, you have to go from right to left, right? So the first operation is U of f followed by R of psi. Now, what is psi? Psi is the input to the initial input over here. So psi is the Hadamard gate creates this uniform superposition, right? So 1 over square root of n summation over x. That is the initial input to the whole Grover operations. It's a uniform superposition of all the sets. So this is the top n qubits is in the state psi. And R of psi, so R psi is this operation minus identity. And what does R of psi do? It actually reflects about the vector psi, where psi is this uniform superposition vector. And you can see that by the definition of R of psi, if I input R psi, if I take the vector psi itself, then it will give back psi. If I take a vector which is in the orthogonal complement of psi, then it will be minus psi. Right? So R of psi reflects about the uniform superposition vector psi. And we will look at the detailed circuits of these two operations later. But for the time being, let's see how does these applications of the Grover operator G help us find the marked element. Now, the querying operation to the database is present within the G operator. So the number of applications of the Grover operator will be our query complexity. Okay, so now let's write psi. So psi is the input to the Grover circuit, right? Is this summation over x. And I can write this, rewrite this as psi is equal to 1 over square root of n, and then summation of x such that f of x is equal to 1x plus summation of x such that f of x is equal to 0. Right? So I have divided the uniform superposition into all those vectors that are marked and unmarked. Now this is a vector which is contains all the marked vectors, but it's not normalized. So and similarly this vector. So let me rewrite this psi in a different way. So I can write psi as square root of m over n psi s plus square root of n minus m over n psi s perp, where psi s is 1 over square root of m summation over x, f of x is equal to 1, x and psi s perp is equal to 1 over square root of n minus m summation over x, f of x is equal to 0, x. So these are two normalized vectors that, and I've written the uniform superposition vector as a linear combination of these vectors. The visual picture looks like this. So let me rewrite it on the next page because I will need some space over here. So let me just write the visual picture is the following. So this is my psi s, and this is psi s perp. And it's easy to see that psi s and psi s perp are actually orthonormal to each other because we have an orthonormal set in the uniform superposition. And our vector psi is a linear combination of these. So maybe somewhere over here. So sorry. So my vector psi, which is our input vector, uniform superposition, is some linear combination of this. And the angle over here, let me call it theta by 2. And you can see over here that from this equation over here, that theta is related, sine theta over 2 is equal to square root of m over n, right? So that's the angle that psi creates with psi s per, right? From this equation, it is clear. Now, that's the input to the Grover operator. Now, the Grover operator itself is a combination of two operators, u of f and r psi, right? And we first apply u of f, then apply r of psi. So u of f marks the marked element. So what does it do? So if I have psi and you apply u of f, it will go to, this will be minus psi s into square root of, so I should write here minus square root of m over n plus square root of n minus m over n psi s per. So what u of f does is that the component of psi in the direction of psi s per remains the same, whereas the component of psi in the direction of psi s gives a negative sign, gets a negative sign right over here. So that means that it actually is reflecting about the vector psi s per, right? So one application of u of f, psi gets reflected about psi s. So this is theta over 2. So that is what psi s perp does. And as I mentioned earlier, that r psi actually reflects about the vectors psi. So when you apply r psi followed by u of f, then there is a reflection about psi. So now this red vector, when applied to r of psi, will get reflected about this vector and will land up over here. And this angle is going to be theta, right? So look what has happened in one application of the Grover operator G. The vector, initial vector psi is now propelled towards the solution space. And that has happened by applying two reflections. So this is reflection 1, which is a reflection about psi s perp. And this is reflection 2, which is the reflection about ket psi, right? And both these reflections combine to give a rotation of angle theta, which is in the direction of psi s. And the goal is to reach this solution space by many applications of this Grover operator. So in the next iteration, this vector will first get reflected again about psi s perp, and then get reflected about psi to get to an angle which is over here. So this will be another theta over here in the second. So this is g square of ket psi, right? And so the question is, how many applications of G do I need to reach close to the solution space? Now, if I take R as the number of rotations, and each rotation gets me further along by an angle theta, and this should be less than equal to pi over 2. So pi over 2 will be the maximum number of rotations that we need to apply. And we'll assume that theta is small because since m is very, very less than n, and sine theta over 2 is equal to square root of m over n. If theta is small, then sine theta over 2 is nearly equal to theta over 2. And so theta is nearly square root of 2 square root of m over n. So if I want to get close to the solution, I should not need more than r less than pi over 2 theta, which is equal to pi over 2 into 2 square root of m over n, which is, so r should be less than pi over 4 square root of n over m, right? So this with square root of order of square root of n applications of the Grover operator, we reach very close to the solution. Now, in the next video, we'll look at a little more detail on this analysis. In this video, we gave a rough idea of what the Grover search algorithm is and how it can quadratically speed up the search.